In this lecture, we will be discussing about the various solar radiation measuring instruments. We know that all the solar power generation systems depends on the availability of solar radiation. Solar thermal electric systems and solar photovoltaic systems performance depends on the availability of solar radiation. So the amount of solar radiation affects the performance, efficiency, maintenance, etc. of such systems. So it is very important to measure the solar radiation. So in this lecture we will be seeing some of the solar radiation measuring instruments. So first one is the pyranometer, and a pyranometer is used for measuring the global radiation or the total radiation over a hemispherical field of view. So it can not only measure the global radiation but also the diffused radiation can be measured. So if we are providing a shading ring to this pyranometer in such a way that it prevents the direct radiation, then we can measure the diffused component of radiation also. So that means a pyranometer can be used either for measuring the global radiation or for measuring the diffused component of radiation. So next one is the Pyrheliometer. So Pyrheliometer consists of a tube which is aligned in the direction of sun's rays. So this can be used for measuring the direct or beam radiation. And another one is the sunshine recorder. Unlike pyranometer and pyrheliometer, a sunshine recorder is used for measuring the duration of bright sunshine in a day. So here these two instruments, pyranometer and pyrheliometer, are used for measuring the amount of sunlight, the intensity of sunlight. But sunshine recorder measures the duration of bright sunshine in a day. For how long bright sunshine is available in a particular day and when it is available. So such things are measured by the sunshine recorder. So now we have to study each of these instruments in detail. So first let us see a pyranometer. So a pyranometer, as we have already said, is used for measuring global radiation over a hemispherical field of view. So it is having a hemispherical glass cover on which solar radiation is falling from all the directions. The solar radiation can fall over this hemisphere from all the directions. That is why we are saying that this pyranometer can measure total or global radiation over spherical field of view, and it can also be used for measuring the diffused component of radiation. So we know that global radiation equals direct or beam radiation plus diffused radiation. If we are preventing direct radiation, then we can measure diffused radiation only. So direct radiation from the sun can be prevented from falling over this instrument by providing a shading ring like this. This shading ring is movable. So as the sun moves along the sky, we can also move this shading ring in such a way as to prevent the direct radiation. So total radiation ഈ pyranometer വെച്ച് measure ചെയ്യാം. ഇനി total radiation ഇന്ന് direct radiation നമ്മൾ ഇവിടെ കവർ ചെയ്യുവാണെങ്കിൽ, ഡയറക്റ്റ് റേഡിയേഷനെ നമ്മൾ പ്രിവെൻറ്റ് ചെയ്യുകയാണെങ്കിൽ, we can measure diffused component of radiation. That is achieved by using a shading ring. So നമ്മൾ ഈ ഷെയ്ഡിംഗ് റിങ്ങിനെ എപ്പോഴും സൺസ് റേസ് വരുന്ന ഡയറക്ഷനിലേക്ക് അലൈൻ ചെയ്ത് വയ്ക്കും. അപ്പോൾ ഡയറക്റ്റ് സൺറൈസിനെ ഇത് പ്രിവെൻറ്റ് ചെയ്യും. So we will get the diffused component of radiation only. So likewise, a pyranometer can measure either total or global radiation or only the diffused component of radiation. So now, how this measurement is done in pyranometer? Let us see. So pyranometers uses thermopile for the measurement of temperature. So what is a thermopile? A thermopile is nothing but a number of thermocouples connected in series. So what is a thermocouple? So you already know about it. A thermocouple is nothing but two dissimilar metals joined together at two ends. So there will be two dissimilar metals which are joined together at two ends. So there will be two junctions, and one of the junctions will be kept at a reference temperature. So we will be knowing the temperature of this particular junction, and if we have to measure a particular temperature, that will be applied to this junction. The temperature to be measured is applied to this junction. Then, depending on the temperature difference between these two junctions, a voltage will be produced across this junction, and we can measure that particular voltage using a voltmeter, and from that voltage we can find out the unknown temperature. This voltage will be calibrated in terms of this unknown voltage. So by measuring this voltage, we can find out the value of the unknown temperature. This is the basic principle of a thermocouple, and a number of such thermocouples are connected together to form a thermopile. The thermopile is used in a pyranometer for the measurement of unknown temperature, that is for the measurement of temperature of the solar radiation. Okay. So here temperature measurement is achieved by using alternate black and white surfaces. This pyranometer sensor will be having alternate black and white surfaces, and the hot junction of the thermopile will be connected to the black coated surface, and the reference junction or the cold junction will be connected to the white surface or the surface that does not receive any radiation. നമുക്കറിയാം പൈറാനോമീറ്ററിൽ ബ്ലാക്ക് ആൻഡ് വൈറ്റ് കളർ കോട്ടഡ് സർഫസ് ഉണ്ട്. ബ്ലാക്ക് കളർ അബ്സോർബ്സ് മാക്സിമം റേഡിയേഷൻ ആൻഡ് white color reflects maximum radiation. So we will connect hot junction of the thermopile to the black surface and the cold junction to the white surface, that is surface that does not receive any radiation. White surface radiation absorb cheyilla. So cold junction will be connected to the white surface, and then there will be a difference in temperature between these two junctions, and a voltage will be induced in this metallic part which can be measured, and thereby we can calculate the value of temperature falling at the hot junction, that is temperature of the solar radiation can be measured. So this is the basic principle, measuring principle in a pyranometer. And in a pyranometer, the induced EMF will be in the range of 0 to 10 millivolt. We can either read it, record or integrate it over time. So now there are different types of pyranometers available. They are Eppley Pyranometer, Yellot Solarimeter, Thermoelectric Pyranometer and Molgorsky Solarimeter. So now we are going to study in detail about the Eppley Pyranometer and Yellot Solarimeter. So the Eppley Pyranometer. So as we have already discussed, the working of Eppley Pyranometer is based on the principle that there is a difference between temperature of black surface and white surface, and that temperature measurement is done by using thermopile. So as we have discussed earlier. So here in the Eppley Pyranometer, there will be alternate black and white color surfaces. The sensor of the pyranometer will be having alternate black and white coated surfaces. So black color absorbs maximum radiation and white color reflects radiation, and the temperature difference between black and white surfaces can be measured using thermopile arrangement. And in older type of Eppley pyranometers, the alternate black and white surfaces were in the form of concentric silver rings which are 0.25 millimeter thick and appropriately coated black and white. So this was the sensor used in the older type of Eppley pyranometers. So we know that there should be alternate black and white surfaces, and they were in this form of concentric rings in older pyranometers. Alternately black and white coated concentric silver rings. And in those pyranometers, 10 or 50 thermocouple junctions were used to detect temperature difference between the rings. And the newer type of pyranometers, the black and white color coated surfaces will be in the shape of wedges. There will be wedge shaped black and white coated surfaces like this. So this is a modern pyranometer where the sensor is in the form of alternate wedge shaped black and white color coated surface. Okay. So this is how you can simply draw the diagram of a pyranometer. So there will be a hemispherical glass covering also. So this sensor, this wedge shaped sensor or this concentric silver rings will be placed inside a hemispherical glass cover. And another important point is that the Eppley Pyranometer is calibrated in a horizontal position. So we have to keep that instrument horizontal for the measuring purpose. It is calibrated by keeping it in a horizontal position. So now next one is the Yellot Solarimeter. So Yellot Solarimeter is nothing but our ordinary photovoltaic solar cell. So we know that in a photovoltaic cell, in a silicon solar cell, which is a PN junction diode, electric current will be generated when solar radiation falls on it. And this current, output current from a solar cell, will be directly proportional to the incident solar radiation. The output current, light current, will be a function of the incident solar radiation. So by measuring the output current, we can find out the amount of solar radiation falling on it. But there is a problem that the spectral response of these solarimeters is not linear. What is spectral response? Spectral response means the ratio of current generated by the solar cell to the power incident on the solar cell. So power in corresponding ആയിട്ട് എത്ര കറണ്ട് ജനറേറ്റ് ആവുന്നു, ഫോൾ ചെയ്യുന്ന സോളാർ റേഡിയേഷൻ്റെ പവറിന് കറസ്പോണ്ടിങ് ആയിട്ട് എത്ര കറണ്ട് ജനറേറ്റഡ് ആവുന്നു എന്നുള്ളതാണ് സ്പെക്ട്രൽ റെസ്പോൺസ്. ബട്ട് ഇറ്റ് ഈസ് നോട്ട് ആക്ച്വലി ലീനിയർ, ഒരു ഡയറക്റ്റ് ലീനിയർ റിലേഷൻഷിപ്പ് അല്ല. സോ വൈൽ കാലിബ്രേറ്റിംഗ് ദ ഇൻസ്ട്രുമെൻറ്റ് we have to consider the spectral distribution of the radiation also. Spectral distribution means which all contents are there in the solar radiation, which all components are there in the solar radiation. ഏതൊക്കെ വേവ് ലെങ്ത് ഉള്ള റേഡിയേഷൻസ് ആണ് ആ സോളാർ എനർജി സോളാർ റേഡിയേഷനിലുള്ളത്, ഏതൊക്കെ വേവ് ലെങ്ത് ഉള്ള കമ്പോണൻസ് ആണ് ആ റേഡിയേഷനിലുള്ളത്. ദാറ്റ് ഇസ് സ്പെക്ട്രൽ ഡിസ്ട്രിബ്യൂഷൻ. So we have to consider the spectral distribution also while calibrating the instrument. The calibration should be a function of the spectral distribution of the incident solar radiation. So spectral response linear അല്ലാത്തതുകൊണ്ട്, that is എക്സാക്റ്റ് ആ സോളാർ റേഡിയേഷൻ്റെ പവറിന് കറസ്പോണ്ടിങ് ആയിട്ടുള്ളൊരു കറണ്ട് അല്ല നമുക്ക് കിട്ടുന്നത്, അത് രണ്ടും തമ്മിൽ ലീനിയർ റിലേഷൻഷിപ്പ് അല്ല. സോ വൈൽ കാലിബ്രേറ്റിംഗ് ദ ഇൻസ്ട്രുമെൻറ്റ് we have to consider the spectral distribution of the solar radiation also. So next type of instrument is the Pyrheliometer. So we have already said that it will be having a tube which is aligned in the direction of sun's rays, and hence a Pyrheliometer measures beam radiation or direct radiation only. Now the sensor for measuring the temperature will be placed at the bottom of this tube. Okay, and here also the measurement is done using thermopile effect. And so we know, we have already said that this Pyrheliometer is for measuring the direct radiation, and it has to be, its axis has to be aligned with the sun's rays for getting the direct radiation. So we know that the orientation of the sun is always changing. As sun moves along the sky, the direction from which the beam radiation comes also changes. So if we have to measure the direct radiation, we have to always align this instrument in the direction of sun's rays. That means there should be a proper sun tracking mechanism. So direct radiation മാത്രമാണ് മെഷർ ചെയ്യേണ്ടതെങ്കിൽ ഈ ഇൻസ്ട്രുമെൻ്റ് എപ്പോഴും സണ്ണിന് എലോങ് ആയിട്ട് അലൈൻ ചെയ്തിരിക്കണം. So for that it needs a sun tracking mechanism, and here in a Pyrheliometer an electrically driven equatorial mount can be used for tracking the sun. an electrically driven equatorial mount. Equatorial mount എന്ന് പറഞ്ഞാൽ എർത്തിൻ്റെ റൊട്ടേഷൻ അനുസരിച്ച് മൂവ്മെൻറ്റ് ചെയ്യാൻ പറ്റുന്ന ഒരു ഡിവൈസാണ് ഇക്വറ്റോറിയൽ മൗണ്ട്. എർത്ത് അതിൻ്റെ ആക്സിസിന് അറൗണ്ടായിട്ട് റൊട്ടേറ്റ് ചെയ്യുന്ന പോലെ ഈ ഇക്വറ്റോറിയൽ മൗണ്ടിനും റൊട്ടേഷൻ പ്രൊവൈഡ് ചെയ്യാൻ പറ്റും. So such an equatorial mount is used for orienting this pyrheliometer along the sun's rays. And here, in order to avoid the diffused radiation from entering into this sensor, a tube is used. This collimator tube used will be having an acceptance angle of 5 degrees. So we will place a tube. So this tube itself. So the tube placed over the sensor. This is our sensor which is coated with black color, and this tube will be having an acceptance angle of 5 degree only. So this is the acceptance angle. So the maximum angle at which radiation can enter into this tube is limited to 5 degree. So direct radiation മാത്രമായിരിക്കും 5 degree angle വരുന്നത്, thereby preventing diffused radiation from entering into the sensor. So we will get the temperature of the direct radiation only. We will be using thermocouple or thermopile for measuring the temperature. And different types of pyrheliometers are Angstrom Pyrheliometer, Abbot silver disc pyrheliometer, and Eppley Pyrheliometer. So first let us see the Angstrom compensation pyrheliometer. So this is the schematic diagram of Angstrom compensation pyrheliometer. There will be 2 manganese strips. One of them will be blackened and shaded, in that it is prevented from sunlight, and the other strip will be exposed to sunlight. So both these strips are connected to 2 thermocouples which are connected to each other in opposition. സോ ഈ 2 സ്ട്രിപ്പും 2 തെർമോകപ്പിളിലേക്ക് കണക്ട് ചെയ്തിട്ടുണ്ടായിരിക്കും. ആ 2 തെർമോകപ്പിളും ഫേസ് ഒപ്പോസിഷനിൽ ഇവിടെ കണക്ട് ചെയ്തിരിക്കുകയാണ്. ദാറ്റ് മീൻസ് വോൾട്ടേജ് അക്രോസ് ദിസ് ജംഗ്ഷൻ വിൽ ബി ദ ഡിഫറൻസ് ഇൻ വോൾട്ടേജ് ഓഫ് ദ 2 ജംഗ്ഷൻസ്. ഇവിടുത്തെ വോൾട്ടേജിൻ്റെയും ഈ ഷെയ്ഡഡ് സ്ട്രിപ്പ് കാരണം ഉണ്ടാകുന്ന ടെമ്പറേച്ചറിന് കറസ്പോണ്ടിങ് ആയിട്ട് ഒരു വോൾട്ടേജ് ഈ തെർമോകപ്പിളിനുണ്ടാവും. ആൻഡ് ഈ സ്ട്രിപ്പ് എക്സ്പോസ്ഡ് സ്ട്രിപ്പിൻ്റെ ടെമ്പറേച്ചർ കാരണം ഒരു വോൾട്ടേജ് അടുത്ത തെർമോകപ്പിളിനുണ്ടാവും. ആൻഡ് ദീസ് 2 thermocouples are connected in opposition. So voltage across this junction will be the difference in voltage of the 2 junctions. Okay, so a galvanometer is placed here. So when the voltage across this will be 0, there will not be a current flowing through the galvanometer, and the galvanometer will show null deflection. And we know that this strip is exposed to sunlight. So when solar radiation falls on it, this strip will get heated. And we can heat this particular strip, shaded strip, by passing heating current through it. So what we will do is, we will supply heating current to this shaded strip until this galvanometer shows null deflection. So we know this galvanometer shows null deflection when there is no current through this junction, through this part. That means voltage across this junction is 0. So ഈ ജംഗ്ഷനിലെ വോൾട്ടേജ് എപ്പോഴാണ് 0 ആകുന്നത്? ഇവിടുത്തെ വോൾട്ടേജും സെയിം ആകുമ്പോൾ, ഈ 2 തെർമോകപ്പിളിലെയും വോൾട്ടേജ് സെയിം ആകുമ്പോൾ. ആ വോൾട്ടേജ് സെയിം ആകുന്നത് എപ്പോഴാണ്? when temperature of both the strips are equal. So galvanometer null deflection കാണിക്കുന്നത് വരെ we will adjust the heating current. So galvanometer null deflection കാണിക്കുന്നു എന്നുള്ളതിൻ്റെ meaning the temperature of these 2 strips are equal. So that means the temperature of our shaded strip will be equal to the temperature of the solar radiation. We can easily measure the energy that we are supplying to this shaded strip because we know the amount of current that we are supplying. So we can calculate the energy of this shaded strip, and that will be equal to the energy of the solar radiation. And the energy of this strip will be equal to K into I square. So it is similar to the equation power is equal to I square R. So here Energy of the direct radiation can be calculated as K into I square HDN, that is heat energy in the direct radiation which is falling on an area which is normal to the sun's rays. So നമ്മുടെ പൈർഹീലിയോമീറ്ററിൻ്റെ സെൻസർ ലൊക്കേറ്റ് ചെയ്തിരിക്കുന്നത് സൺസ് റേക്ക് പെർപെൻഡിക്കുലർ ആയിട്ടാണ് സെൻസറിൻ്റെ പ്ലെയിൻ ലൊക്കേറ്റ് ചെയ്തിരിക്കുന്നത്. സോ HDN മീൻസ് ഡയറക്റ്റ് റേഡിയേഷൻ ഇൻസിഡൻറ്റ് ഓൺ an area normal to the sun's rays, which is equal to K into I square. I is the current that is flowing through the shaded strip and K is the dimension and instrument constant of the pyrheliometer. Its value is equal to R divided by W into alpha, where R is the resistance per unit length of the shaded strip. Resistance per unit length of the absorbing strip. And W is the mean width of the absorbing strip. Width of the absorbing strip is W, and alpha is the absorbing coefficient of the absorbing strip. So by using this equation we can calculate the energy supplied to the shaded strip, which will be equal to the energy of the incoming solar radiation. So next type is the Abbot silver disc pyrheliometer. It consists of a silver disc, here it is marked as D, a silver disc which is coated with black color, placed at the bottom of a tube. So this tube will be having diaphragms. So these are known as diaphragms. These structures are known as diaphragms. So this tube will be having diaphragms which limits the aperture to 5.7 degree. That is, the maximum angle at which solar radiation can enter into this tube will be 5.7 degree. So ഈ vertical direction അവിടുന്ന് ഈ ആംഗിൾ 5.7 ഡിഗ്രി ആംഗിളിലും അതിൽ നിന്ന് മാറി 5.7 ഡിഗ്രി ആംഗിളിലും ഫോൾ ചെയ്യുന്ന റേഡിയേഷൻ മാത്രമേ ഡിസ്കിൽ ഫോൾ ചെയ്യുള്ളൂ. സോ Abbot silver disc pyrheliometer, as the name indicates, will be having a silver disc placed at the bottom of a tube. This is coated with black color and the diaphragms limits the acceptance angle of this tube to 5.7 degree. And for the measurement of temperature, here we are using a mercury in gas thermometer. In all other cases we have used thermocouple for temperature measurement, but here we are using a mercury in glass thermometer, and the stem of the thermometer is bent to 90 degree. So the portion where mercury is filled is connected to the silver disc for measurement, and the stem of the thermometer will be bent through 90 degree and it lies along the tube. This is done in order to reduce the exposure of the thermometer to sunlight. Okay. So measurement can be done using this particular thermometer. And also there will be shutters. There will be shutters made up of metal leaves. There are 3 shutters made up of metal leaves, and we can alternately open or close these shutters in order to allow solar radiation to fall onto the disc periodically. So in order to allow solar radiation periodically, we can open or close these shutters. So next one is the Eppley Pyrheliometer. So in Eppley Pyrheliometer, for the measurement, a bismuth silver thermopile is used, having 15 junctions. So measurement is done using a 15 junction bismuth silver thermopile. അതായത് 15 thermocouples junction ഉണ്ടായിരിക്കും ഇവിടെ. And it is placed in a brass tube. So the limiting diaphragm of the tube subtends an angle of 15 degree. Here also the tube will be having diaphragms, and that diaphragms makes the acceptance angle of the tube 15 degree. മറ്റ് Abbot silver disc pyrheliometerൽ ഫോൾ ചെയ്യുന്ന എൻ്റർ ചെയ്യുന്ന റേഡിയേഷനേക്കാളും കൂടുതൽ ആംഗിളിൽ റേഡിയേഷൻ ഇവിടെ എൻ്റർ ചെയ്യും. ഇറ്റ്സ് അക്സെപ്റ്റൻസ് ആംഗിൾ ഇസ് അബൌട്ട് 15 degree. And so we know what a thermopile is. Here we are using a 15 junction bismuth silver thermopile. So we are coupling thermocouples together, connecting thermocouples together in order to get a very high voltage, in order to get a greater voltage than that is available with a single one. So here the tube the tube will be filled with dry air and it will be sealed with crystal quartz window which is removable. So tube on the bottom of which this thermopile is placed is filled with dry air and it is sealed with a crystal quartz window. ഒരു ട്യൂബ് ഉണ്ട്, ട്യൂബിൻ്റെ ബോട്ടത്തിൽ ബേസിസിലാണ് ഈ ബിസ്മത്ത് സിൽവർ തെർമോപൈൽ വെച്ചിരിക്കുന്നത്. ആ ട്യൂബ് വിൽ ബി ഫിൽഡ് വിത്ത് ഡ്രൈ എയർ ആൻഡ് ഇറ്റ് is sealed at the top with crystal quartz window and this window is removable. So whenever we have to make measurements we can open the window. So this instrument has found wide acceptance within the USA and many part of the world. So that is all about pyrheliometers. And now let us see what a sunshine recorder is. So sunshine recorder is used for measuring the duration of bright sunshine in a day. So we can get informations like how long bright sunlight is available in a particular day and on which all times this sunlight is available. So these factors can be measured by using a sunshine recorder. So this is how a sunshine recorder looks. It will be having a glass sphere and in concentric with this glass sphere there will be a hemispherical bowl. So this is the hemispherical bowl. So this glass sphere and this hemispherical bowl are concentric with each other and on this hemispherical bowl we will place a card. A card will be placed on this hemispherical bowl and on the card there will be markings. There will be scales on this card and when solar radiation falls on this this glass sphere, it will focus the entire radiation into a particular point on this card. So ഇതൊരു ഗ്ലാസ് സ്ഫിയർ ആണ്. സോ ഇതിനകത്ത് ഫോളോ ചെയ്യുന്ന ആ റേഡിയേഷനെ മുഴുവൻ ഈ സ്ഫിയർ ഇതിൻ്റെ താഴെയുള്ള ഈ കാർഡിലെ ഒരു പെർട്ടിക്കുലർ പോയിന്റിലേക്ക് ഫോക്കസ് ചെയ്യും. So the intensity of that solar radiation which is focused on to this card strip will be very high so that it burns that particular point on the card. So that point onto which this entire radiation is focused will be burned due to the intensity of that radiation. And as the sun moves along the sky, the image formed in the card, that is that burned space moved in the card, also moves along the strip. And at the end of the day, by measuring the length of the burned space, we can find out the duration of bright sunshine in that particular day. So this glass sphere concentrates entire sunlight to a particular point and the intensity of that sunlight will be very high. It burns that particular point on this card. Okay, and as the sun moves, the point on to which this light is focused also moves. So a burned space will move. So we will get a particular length of burned space along this card. This card will be having scales. By measuring the length of that burned space, duration of bright sunshine can be find out. So this is the diagram of some card strips which are obtained from a sunshine recorder. So different days ഒരു sunshine recorder നിന്ന് കിട്ടിയ card strips ആണ് ഈ കാണിച്ചിരിക്കുന്നത്. So look at this strip. This will be having a greater length of burned space. That means, so this strip corresponds to a day having a very bright sunshine. Okay, it may be from a day in a summer season, and in this card we can see the burned space at some times. Okay, at some points of the card there are burned spaces. That means sunlight is available on that day. Sunlight is available periodically. Sunlight was intermittent on that day, and on this card there is only three burned spaces. That means sunlight was available during a very small period on that particular day. And if we consider this particular strip, there is no burned space in this strip. That means no sunlight was available on this particular day. So that is how a sunshine recorder works.